So stability is, remember all the way at the beginning of this semester. Remember I had the pendulum, we started out with the pendulum, remember? Seems really long time ago, but we really started with the pendulum. So we said we start from an initial condition, we said this is an equilibrium point, right? We start here and then we leave it and then it will oscillate and it will come back to the equilibrium point, right? This is what we call the stability of the equilibrium point. Basically, is the tendency of the pendulum to come back to the equilibrium point. We call it static stability, right? The static stability characteristic. How long does it take to come back? Will there be oscillations? All these questions, these are dynamic stability characteristics, right? So, in static stability, we disturb the system from the equilibrium point and see if it wants to come back. And without controls, without touching the controls. Because, the control for the pendulum was that force that I could just move that thing with my hand, right? So which really means that, if this is the equilibrium point, with my hand I could actually move it the way I want, right? That's not a stability characteristic. Control is just, I can control it with my hand. Stability is just, will it come back? Without touching it, will it come back to the equilibrium point? So it's the same thing for the aircraft. You disturb the aircraft from its stability, from its equilibrium point. How do you disturb it? Anyway, there could be a little control input so that the aircraft is not at the equilibrium anymore. It could be a wind, it could be a gust, it could be some turbulence. It could be Superman. You know Superman? You're flying, Superman can just touch the wing, and it's now away from the equilibrium point. Question it, will it come back to the equilibrium point without ever touching it again? Disturbing, will it come back? Disturb it from the equilibrium, will it come back? Sometimes similar in your life. You have some sort of stability in your life, right? But sometimes you have a disturbance. Something happens in your life and you are not on track anymore. Well, hopefully you are stable enough to come back on track and move on with your life. Right? If you diverge from your path, that's not good. Right? So everybody loves stability. All right? So it's very similar. Of course, people will try to help you to bring you back to track. But the question is, without anybody's help, will you come back automatically? In other words, do you have a stable life? Okay? Important stuff. You have to think about it. All right. So stability and control, they move in different directions. Because in order to go away from the stability, from that equilibrium point, you need to have control. So in other words, yes, if there's a disturbance, you will come back from your side slip or from your roll angle. The question is, sometimes I really want the roll angle, right? Why do I want the roll angle, for example, to turn, right? Let's say this is the airplane, and I'm flying like this. That's my wing. And this is your lift. And this is your weight. And hopefully the lift and the weight is the same approximately, all this stuff with small angles and so on and so forth, and you're flying forward. So when you rotate, you want to rotate, and your lift looks like this now, and this is your weight. So hopefully, what happens if this lift is the same, what's going to happen now? You're going to fall down? Yeah, you're going to fall down because the lift was balancing the weight. Now the lift cannot balance your weight anymore because this is not good enough. So what do you need to do? The aircraft has to increase angle of attack or increase velocity somehow to increase this lift so that this component is still equal to that. And you have this component for what? What is this component used for now? So that the aircraft can make a turn, right? Now this is a centripetal force. So if you look from the top, you will see an airplane that is rotated to the side and actually has a centripetal force towards the center. Okay? So where is that force coming from? That force is coming from this one because of that turn. Right? Otherwise you cannot turn. How would an airplane turn if you don't have that side force? That side force is coming because, a side force is not a good word, because side force kind of implies a force in the direction of YB, right? And there is no force in the direction of YB really. Lift is still perpendicular, right? This is in the direction of, in this direction. But this here is YB. So in order to make that turn, you need to turn that aircraft. You understand that, right? Look up here. If this is my airplane, I'm going forward, and I want to make a turn. And if this is the center of my rotation here, you need a centripetal force, right? Without that centripetal force, you cannot turn. So where's the centripetal force coming from? Someone has to pull you inside. So who's going to pull you inside? If this is the lift vector, and you rotate, now you have a component in that direction because of that lift vector, and that component will start rotating you like that. Okay? Without that rotation, there is no side, the centripetal force is not there. Right? You fly like that. So in certain cases, you need that phi, especially if you want to make a turn, you need that phi. So where is that phi going to come from? The phi is coming from the controls. The pilot will induce that phi. So that's my topic, is therefore roll control. Okay? And the roll control really comes from ailerons. All right? We call them ailerons. So what does it look like? Well, you know that probably already. This is my wing. Okay? So this is the back of my wing, and at the very tip here, you have these pieces. Okay, this is one is going up. This one here is going down. I didn't do a good job plotting this, but this looks a little better. Right? This one is going up. So going up, this is up. Let's call this delta 1. This is an angle. And this one is going down. Let's call it delta 2. So the right side, this is the right. The right side of the wing is, if this is down, the left side is up. Okay? And this one we will call a positive del A. So right is down, right down, left up. We call it a positive aileron input. Okay? Sorry. We call it a positive aileron input. Okay? And del A, this aileron input, is really this. 1 over 2 delta 1 plus delta 2. So it's kind of the average. Okay? So for most airplanes, of course, delta 1 and delta 2 are equal. Right? You want to do it in a symmetric fashion. One goes up, one goes down, so they're kind of the same angle. But it doesn't have to. Okay? There are cases where it's not the same. It doesn't have to be. So what would I call an aileron angle? I would call the average. Okay? And this is, of course, okay, this is positive, good. So for most airplanes, they are kind of the same. All right? And this is what we call an aileron angle. Basically, that average here is called the aileron angle. So you look at airplane, so this is where the fuselage is, right? It's in the center. And you put the ailerons all the way to the wing tips. Why do you put it to the wing tips? You put it to the wing tips because you want to have that large moment arm, right? Let's say the aerodynamic center are here. This is the aerodynamic center of the ailerons, right? So you have that large moment. So if this goes down, what does it do? It is like increasing the camber on this part of the wing, right? If you look at the wing from this side, it will probably now look like this with the aileron going down, right? This is down. And on this side, it will go up, so it will be more like that. So on this side, you will definitely have more lift because it's going down, more lift. And this side, you will have less lift. Okay? And therefore, you will get a moment like that. Okay? So, question then. Del CL del delta A. Positive or negative? It has to be negative, right? Because if this is a positive situation, which means the right one is going down, the left one is going up, more lift on the right side, less lift on the left side, which means you have this is a negative moment, negative rolling moment, because if this is XB, so you take your right-hand rule again, right? This is a negative moment, and therefore you will get for a positive del A, you will get a negative CL. So therefore, this is a negative number according to our sign convention, of course. If you change the sign convention here, saying that this is a negative del A, then it will be a positive. But with this sign convention that we use in flight mechanics, this would be a negative partial derivative. Again, that was a good question that I think you asked during the break. This is still a partial derivative, which means everything else is constant. What happens to del CL when I change del A? It's still a partial derivative, everything else being constant. Okay. Okay, so any questions up to here? All right, so here's my wing again. You have your positive aileron over here, negative over here. Okay, let's say del A is positive, which means you have more lift on this side, less lift on this side. But as you probably can guess, it also means more drag on this side and less drag on this side. Isn't it? Whenever there's lift, there's drag. Less lift, less drag. So more lift means also more drag. So what does it do to the wing because you have more drag on this side? It will also have a yawing moment because of this. Isn't it? More drag on this side, which means more drag, less drag. What's going to happen? You are going to have a yawing moment, isn't it? More drag, less drag. More lift, less lift. So, is this a positive rolling moment, yawing moment, or a negative yawing moment? That is a positive one. If you're looking from the top, right? That's a positive rolling moment. So del Cn, del A, positive or negative? Positive. Okay, very good. You're doing very good. You kind of got the feeling for it, right? The feel. So, more like so you're rotating like that. Is that a good thing or a bad thing now? Seems like a bad thing because, you know, if you get more lift on this side, less lift on this side, looking from the back, okay, more lift, less lift. This is now looking from the back. sorry, looking from the back, more lift, less lift. So the aircraft really is going to turn in this direction, right? So the airplane wants to do this. Okay? And because of that, what I just explained to you, this will be now your total lift, and you really want to turn looking from the top. Looks like you will be turning in this direction, like that, right? You will be turning like that. This is your rotation. However, look at the drag. The drag is more over here and less over here, and actually try to rotate you in that direction. It is actually trying to rotate you in the opposite direction, you see? It's actually not a good thing. You understand what I'm saying? Let me try to explain it to you again. More lift on one side, less lift on the other side. More drag on this side, less drag on this side. So looking from the back, more lift over here, less lift over here, which means the airplane wants to rotate in that direction. So if the airplane rotates like that, it obviously wants to turn like this, right? That's what we want, isn't it? Say yes or no. Yeah, okay. So lift like that, less lift over here, so you rotate, and when you rotate like this, lift vector in this direction, we start rotating like that. However, if you look at it, more lift also means more drag. So you rotate like that, yes, more lift over here, but also more drag. So I want to do this and rotate like that, but drag is pulling me in this direction. Not good. That's what I'm trying to say here. More lift, rotate like that. Okay, that's good. Looking from the top, I want to move in this direction, but more drag in this direction, so it's trying to move me over here. You see? This is what we call adverse yaw. Adverse yaw is not good. Because you do this, you want to rotate in this direction, but in order to do that, you get more drag on this side, and it's pulling you in that direction. Okay? Not good. This is what we call adverse yaw. Yaw in the wrong direction. Now, this is not really a problem if that drag is not too big, right? I mean, if the drag difference is not too big, it's not really a problem, which means if the lift difference, if the difference between these two lifts are small, okay, look up here. If the lift difference is small, which means the airplane is slowly doing this, which means the difference in lift is really small, then the difference in drag will also be small, right? And you have that adverse yaw the adverse yaw will be small. But let's say you make a fast turn, meaning the lift on this side is really big, the lift here is really small, and then the difference is large, so there's a large difference in the drag, you really have that adverse yaw. That happens if you make a fast turn with big wings. Okay? Big wings means big moment arm, lots of lift change or lots of lift difference. There will be a lot of drag difference, big wings, big forces, fast turns. The difference is large, therefore the difference in the drag is large, and you have that large adverse yaw. For most passenger airplanes, you look at the passenger airplanes, the rotation is really slow. It's a little bit of a change in the aileron and you start rotating like that. You see? Okay, so that's adverse yaw. So how do you get rid of adverse yaw? What can you do? Well, if you have if you have a really big wing and adverse yaw is really a problem. As I said, for most airplanes, it's not a big problem if you make these rather slow turns. But if it's a really big problem, what can you do? One of the things you can do is, let's say your aileron is moving in one direction and the other one's moving in the other direction. Let's say you have high lift and therefore you have high drag, and here you have less lift and less drag. Okay? But you want that lift difference, but the drag you don't really like. What you can do is you also want to have more lift on this or more drag on this side. What you can do is you can put a spoiler over here. Okay? This is what we call a spoiler. The spoiler will also, of course, be also on the other side. Okay? Spoiler. A spoiler is basically something that, as the name suggests, it spoils the air, which means the air is no more attached. It kind of changes the air, right? So it also increases the drag on this side. So it will be, it's something like that. If this is your airfoil, okay, this little spoiler is here. Let me put it here. Spoiler is here on the wing. So when you activate the spoiler goes up. So the airflow that was normally flowing nicely like that cannot flow like this anymore. It actually does this. So in here, you get all the drag you want. Okay, generating drag is easy. You just have to mess with the V infinity a little bit and you suddenly have drag. So this can go up and down very quickly, the spoiler. So momentarily, while you are activating this, the ailerons, the spoiler, look up here, might slowly go up and down, just slowly, just very fast. So for momentarily, you get extra drag from the spoiler, so you can adjust the adverse yaw. Okay? So if you come back here and you have that drag difference, all you need to do is get more drag on this side. You open the spoiler momentarily, get drag, and then close it down again. And then you counteract that adverse yaw. Of course, if you have it too long, what happens then? Then you also lose lift on this side, and the airplane gets into real trouble because now you lost all the lift on the wing, which is not good, of course. But momentarily, you could do something for that adverse yaw. You might have seen on airplanes these little things that sometimes go up and down, the spoilers. Sometimes because of that adverse yaw, and sometimes you can even adjust the heading with it, right? A little less lift and drag and all this. Especially, the spoilers are very useful when you land, okay? So what do you want when you land? The worst thing is, look up here real quick. When you land, after you put the landing gear to the ground, you don't want the aircraft to lift again because you are getting into a real dangerous situation. You are very close to the ground. And if you do things wrong and you lift again and you roll, you really don't have much margin to move when you're up in the air again, right? Because you are so close to the ground. So you're already put your feet on the ground. So you just want to stay on the ground firmly and slow down the aircraft, okay? So in that very moment, you will see the airplane, if it's a big airplane, has spoilers, it immediately opens the spoilers and leaves them there to really remove the lift. So you want to have them open very quickly so that you remove all lift and also generate a lot of drag to slow down, but at the same time not to take off again. Imagine that one wing is a little faster than the other one. That would be really horrible because then you would have more lift on one direction and less lift over here when you land. For whatever reason, if you have more lift on one direction, you might immediately be doing this with the airplane. You don't want that. When your feet is on the ground, you really want no more lift, lots of drag. The best way is to open up your spoilers and really slow down and no more lift. You really want to be on the ground very firmly. You know, when we fly, we always want a lot of lift. But when you land, you want no more lift. Lift must be gone. Understand? So, okay, one more thing. You know, a lot of times when pilots land the aircraft, and when the pilot makes a really soft landing, okay, passengers are very happy. They always say, "Oh, that's such a good pilot because we made such a soft landing." Well, it's not really the best way to land. The best way to land is really smash the airplane onto the ground very firmly. Open your spoilers so that you don't take off anymore. Sometimes I see a pilot landing very softly, and then I see a little bit of lift off after that and puts down again. It's very dangerous, actually. The passengers, they like it because it's very soft, but that's not a good thing because you don't have much margin to maneuver when you're on the ground. What you really want, you want to be firmly on the ground and never take off again and put your nose down and slow down as fast as possible, right? So if you have the soft landing that kind of does this, it's not a good thing. So you might see if there's a lot of side wind or there's a lot of turbulence, a bad weather, a good pilot would just smash the airplane on the ground, put the landing gear firmly on the ground, and then go on the ground. So you open up the spoilers, which will remove the lift literally, okay, and at the same time have a lot of drag to slow you down. Is that good? Okay. What else? What else? The adverse yaw, of course, becomes quite important or more significant, as I said, if you have big wings. When I say big wings, I kind of mean high aspect ratio wings, you know, when you have these really long wings with ailerons over here and the large moment arm, high aspect ratio. This adverse yaw becomes kind of a problem here. Okay? So, that's that. Another thing I want to tell you a little bit about is you might have seen, if this is your fuselage here, you might have seen a lot of stuff happening here as well. Okay? Usually on most airplanes, we'll look at pictures again. These are usually the flaps. I mean, you could put controls over here as well to help the ailerons. Okay, these are the ailerons. Ailerons. Okay, these are the ailerons, and these are the flaps. The flaps have a totally different purpose, of course, right? If the airplane flies like this in air, the flaps basically is this part that goes out a little bit and then actually does this, right? So you have this part, and it's kind of like this part is kind of over here, kind of hidden here. So this will come out and actually turn down and make it look like this. So why do we need that? This is in order to increase the surface area, right? But also increase CL because of the camber here now. In fact, increase CL alpha, right? Because the camber, the original camber was something like that. Now you have a camber that actually looks like that. Look at this. Right? Large camber. So you increase CL alpha, but you also increase S. And this is what flaps are doing. And they are there to generate more lift, of course. Right? More CL alpha, more camber, more surface area, more lift. Look at the lift formula, right? 1 over 2 rho v squared S, and CL alpha is there, of course, as well. So why do we need that? We need that to generate the same lift with at lower velocities. If you look at the lift formula, of course, CL alpha times S. So if velocity is going down, right, these two need to go up and alpha needs to go up. And that's what happens during landing, right? An airplane is flying approximately 900 kilometers per hour, a passenger airplane, when you're flying when you're flying 800, 900 kilometers per hour. You cannot land at 900 kilometers per hour, so you are landing at 200, 250 kilometers per hour. But you still need the same lift. You know, we had that discussion, I think. The lift should still be approximately equal to the weight while you're landing. That's always the same question, right? If an airplane is in landing and has no acceleration and constant velocity, is it in trim? Yes, of course, right? Which means the forces and moments are still equal to 0. So when I ask this the first year students, you know, in 101, I say, what happens here? They say, oh, lift must be much less because it's landing. That's not true. If lift is much less, that means there's a lot of weight and you have a lot of acceleration, so you go faster and faster. But if you want to land with a constant velocity, with a constant descent rate, then the lift must be really equal to the weight. Isn't it? So that means that at slow velocity, at 250 kilometers per hour when you're landing, you still need the same lift as your weight, which is the same when you're flying 900 kilometers per hour. The difference is that V infinity now is a lot smaller. So what do you do during landing if this is really small? You try to increase everything in your power. You increase alpha, so you see the airplanes landing like that, like that, with a lot of angle of attack, right? But angle of attack has a limit because if it's too large, you go into stall. So you have a limit. So you go very close to the stall angle. But then you can increase CL alpha, meaning that you increase the camber, right? And that's what you do with your flaps. What else can you do? You can increase the surface area, so the flap helps you with increasing the surface area as well. So you increase everything that's in your power. And that's why you need the flaps. And the flaps are usually in the rest of the wing. I mean, you have the ailerons at the tips, and the flaps there are, and the rest of the wing is usually filled with flaps. If it's a typical passenger airplane. Not every airplane has to have a flap, of course. If it's a small airplane, it can probably land without flaps. Okay? But all I'm saying is that if you look at the wing, I will show you a few pictures in a minute, but if you look at wings, you have to distinguish between ailerons and flaps. A lot of times, you know, people who are not in our business, they might think that, oh, here are the ailerons because they have all this stuff. No. Aileron is this little piece at the tip. The rest is the flaps. In really big airplanes, you might see that the ailerons are, first of all, 80 questions up to this point. Okay. There's one more thing I want to tell you regarding the ailerons and roll control. You know, if you have really big wings, long wings with high aspect ratio, and let's say this is your fuselage here, what happens is this wing here is not really a rigid body. As the wing becomes larger and larger, look up here, the wing has its own flexibility. Okay? So it might so happen that during flight, the wings are kind of oscillating. Okay? Even if it wasn't flying and you had the airplane in the hangar, if you hit that wing, it would be doing that, right? Now, when the wing does that, it is interacting with the air, of course, and you're going forward. Imagine at the moment when the wing is going down, it increases the angle of attack, isn't it? So suddenly you have more lift, because of that movement. The wing, if the wing is not rigid like this and the airplane is oscillating because of the structure, now oscillation is not done by itself. When it's going down, it increases the angle of attack. When it goes up, moves up, it reduces the angle of attack. Because when it's going down, you have a relative wind coming from here now, right? Do you understand that? So when it oscillates, it changes the angle of attack. The angle of attack actually starts changing because of that movement. And the airflow is not necessarily steady at that point because it's moving a lot maybe, then it becomes unsteady. And the interaction between the structure and the aerodynamics can be quite dangerous at sometimes. This movement we call flutter. Okay? So it's an aeroelastic problem. It's the structure plus the aerodynamics that interact together that could potentially, not always, potentially cause this to resonate. If it's in resonance, then you can actually break your wing. Okay? Because that oscillation can increase, and it can break your wing. So we don't want flutter, and we want to have these oscillatory modes, these aeroelastic oscillatory modes, we want them somewhat in control. You see? We don't want to leave it alone. How could I control this movement on the wing? One way of controlling it is actually with ailerons. You can move the ailerons or oscillate them in such a frequency such that it will counteract this mode. You see? You understand that? So if the wing starts oscillating, you can take the aileron and go in the opposite direction and try to remove that oscillation. It's like noise-canceling headphones. Yeah? You measure the noise, and then you take the frequency and the amplitude and reverse it and give it as an input. It will cancel the noise, and you will not hear anything. It's very similar. You can cancel vibration with another vibration, with another oscillatory input. You have seen this in vibration, right? Everybody's taking vibration? No? Why not? What? Oh, yeah, you're 30, that's right. Okay, I'm sorry, I'm getting confused. You can cancel oscillation with another vibratory input. So the aileron can actually move a little bit like that and cancel that oscillation. So you could use the aileron for structural, in order to avoid those things, those vibrations. Now, if you have a really big wing, listen, if you have a really large, big wing, imagine the A380. You know the Airbus 380? It's a huge wing, huge airplane. I mean, that wing probably has really a lot of aeroelastic modes. So you need to suppress those modes. And an aileron over here might not be enough to suppress those modes. So what do? You have that little thing here, but you might have a few control surfaces over here as well, or maybe somewhere over here. Again, control surfaces, not flaps, just things that move up and down. And you wonder what these things are. Well, they can help you to maneuver, of course, but they can help you also move them up and down, and you can suppress some of the structural modes, the aeroelastic modes of the wing, because you don't want the wing to oscillate too much and become dangerous. Okay? So if you look at the wing, you see a lot of stuff. You see the flaps, you see the spoilers, you see the ailerons. You know, it's kind of crowded there. And sometimes, one more thing, you might have pieces in the front. They are very similar to the ailerons. Not ailerons, I'm sorry. They are similar to the flaps. They just go to the front and they actually do that. Right? And they are actually increasing this even further, the CL alpha. Okay? So that's what's happening on the wings. Any questions? Yes, sir.
Are these flaps on these notes actually helping with the CM alpha?
Oh, what happens to the CM alpha? That's a very good question.
CM alpha increases.
Yeah.
It should be a negative value, but in the landing or the takeoff, during the takeoff, you don't want to actually do this motion. So you want a CM alpha bigger, right?
Right. Right, which means you really have to play with your horizontal tail. All these things that I explained to you, listen, all the things I explained to you with the flaps, ailerons, slots, everything, they will also have an effect on CM alpha. I never really talk much about the moments, but it will change the moments. But fortunately, you have the horizontal tail that is used to adjust everything you need in terms of the pitching moment. Okay? So if there's something that's happening with the moment that you don't like, you always have the choice to adjust it with your horizontal tail. Now the horizontal tail, or the control on the horizontal tail, it must have enough power or enough power in order to adjust for everything. So when you design your aircraft and you have a moment coming from these things, and you don't have enough moment from the horizontal tail, then you can't fly the airplane. So as flight mechanics engineers like you now, you have to make sure that whatever moment is created from these things, you have to be able to adjust it or trim it with your horizontal tail. Okay? Because if you cannot trim it, then you have this like that. Did you see the movie Flight? With Denzel Washington? Haven't seen it? If you haven't seen it, you go and see it again. What happens is the horizontal tail is getting stuck. So he gets a nose down. And he can't pull it up because the horizontal tail doesn't work. And he has his nose down moments. So what does he do? He flips the airplane, and now he has a nose up moment coming from the tip. Right? But if you adjust it with the throttle nicely, then you can still fly with a high angle of attack like that. That's what he's trying to do, but in a reverse flight. And in the last moment, he's rotating and try to land. So he's saving a lot of lives. But it's an interesting movie in terms of flight mechanics. Okay? So go and watch the movie if you haven't watched it. I don't know how many people have watched Top Gun or have not watched Top Gun. If you haven't watched Top Gun, you need to go and watch Top Gun. I don't understand an aerospace engineer without watching Top Gun, Flight, or any of these movies. Any questions? Yes, please.
Are these all adjustments under pilots or under the
control
of the aircraft?
Yeah. In the old times, these are good questions. Listen, in the old times, this was all done, of course, by the pilot. Right? The pilot has to do everything. But recently, I mean, in the past 20, 30 years, the control systems, the autopilots take care of most of these things now automatically. The pilot is only there, not only there, but the pilot, we want the pilot to tell the airplane what to do. You know, want to go straight, want to nose up, want to turn to the side, want to make a turn, you know. But all these little tiny things should be taken care of in the control system. So the adverse yaw stuff, for example, the pilot shouldn't really be thinking of activating the spoiler because of adverse yaw. He wants to turn, so let him just do this, and he turns, right? And then the autopilot will automatically turn on the spoiler for a moment to remove the adverse yaw. So a lot of stuff now is really happening in the autopilots, in the control systems. So if you look at a commercial airplane now, the pilot really takes off the airplane, but after that, he puts it to the autopilot, and even the turns are done by the autopilot. Doesn't do the turns anymore. You know, if a pilot really wants, he can actually take off from Istanbul, you know, switch on the autopilot. In the flight management system, it will just tell the waypoints, the points it will follow in space, and sleep with you in the airplane, and then wake up when he's in New York and then do the landing. So the whole thing can actually be done with the autopilot. And that's actually what happens most of the time. The pilot doesn't fly these things per se. Okay? And it's just getting more and more automated. If you think about it, an airplane can also take off and land automatically. So the question is, do you still need a pilot? Well, tell the passengers that the airplane doesn't have a pilot. You know. But more and more, we call it a pilot's workload. We are trying to reduce the pilot workload, because otherwise the pilot has to work a lot. So we want the pilot to concentrate on the important things, not on the little tiny things that we can take care of in the autopilots. Another thing is, of course, emergencies or malfunctions. If something goes wrong, you really need a good pilot to take care of things when things are not going the way you intend to be. Okay. Any other questions? Okay, let me show you a video. I found it on YouTube, so it was there are lots of videos, but it is something that it's nice to discuss things when you know more. Flaps over here. And you see during takeoff, the flaps are a little bit down, not too much. You need more flaps when you land, right? When you want to take off, you want to go as fast as possible. So you recognize the dihedral a little bit now? Look at the flaps. See the flaps? These are the flaps. They are down, not too much. This is the aileron here. That little piece, that's the aileron. Is that okay? All right, landing. See the flaps? They're quite down a lot more. Okay? Here at the back, you will see the ailerons. You see, you have a rather high angle of attack. Of course, from this picture, can you tell if there's angle of attack or not? No. If I just show you that picture, you cannot, because the airplane might be going like this, and it might have zero angle of attack, right? So never get fooled looking at the picture and say, oh, lots of angle of attack. Look at this. What is this angle? It's the pitch angle. It's theta, right? Doesn't mean it's angle of attack. And I can say this is theta because there is no roll angle. If there was roll, then what would be theta? Roll, and then that's theta, right? Okay. You see these little things here? These are Pitot tubes. The Pitot tubes are here. You need to measure V infinity. Who's going to measure V infinity? How many of them do you have? You have usually at least 4 of them. 1, 2, 3, 4. Because if one is malfunctioning, you still need V infinity, right? The measurement of V infinity. Okay. Oh, that was a good one. You just missed it. That's a Boeing 777, so it's a large airplane. Look at this. Look at the flap. Can you imagine the drag coming from the flap? Look at this one, still flap. Lots of drag. Look at the spoilers. You want a lot of drag, very little lift. Ailerons here. That piece. The rest is just trying to reduce lift. A lot of drag, of course, now. I mean, when it was landing, it wasn't probably that high. Okay. So larger airplane. Do you see the dihedral? It's not much, but it's there. You see that angle? Still there. You see these pieces here at the back? They are pieces of the flaps. In order to bring it down and have this much resistance from the air, you need these strong structures. Look at the front. It's kind of tilted a little bit to the front. You see the front? It's just to make CL alpha bigger, more camber. Look at the position of the horizontal tail. It's up here and the wing is here. Someone was telling me during the break, why can't we steer the landing gears during landing? Well, look how big these landing gears are. These landing gears are huge, okay? And when they land, they absorb a lot of load and energy. If you start making them rotating, it will be a very difficult landing gear design, I guarantee you. And probably will weigh a lot. Do you see my Pitot tubes?
Why do you use Pitot tubes on the realm of the aircraft, but not nearby beams? Because beam could change due to disturbance of the aircraft. So why do we use them in front?
Not on the wings?
We use also
No, not really. But because we are interested in the real velocity of the air. See, what happens if you can put them on the wings, there's no problem. But when the airplanes start doing this, one Pitot tube will measure more than the other one. So you are also measuring that rotation. Okay? There were cases where I've seen people trying to measure that rotation from V infinity, but that's a little not very reliable. It's not useful. There might be wind coming from this side, no wind on this other side, and you might be thinking you're turning and all this stuff. What you're really interested is what is the pure V infinity that this fuselage will see. What you're seeing here, there's more stuff, of course. There's these stuff and there might be some other stuff. You're not only measuring V infinity. That's not only Pitot tubes. You only measure temperature. You measure temperature. Very important. Okay? Temperature, V infinity, and sometimes these bigger airplanes, they also measure angle of attack. They have a little angle of attack measurement over here. Okay? All right, want to give a break? Okay, let's give a break and I'll get back to this.